So, hello and thank you for being there. I'll be presenting, firstly, I'm Julien, PhD student at Laboratoire Mercurial, and I'll be talking about what I've done at the start of my PhD thesis in the Ultracam project, meaning ultrafast laser structuring for topological and chemical functionalization of surfaces. So firstly, I'll talk about what the Ultracam project is, firstly, so its context, the scope and goals, what's already been made in previous, for instance, PhDs at Laboratoire Mercurial, and then I'll sum everything up on project. Then talk about what's already been done on the experimental side during a campaign of 3 weeks in October, and then I'll talk about what makes really this project special, meaning what I call ultrafast high temperature oxidation. I'm still doing research on that, but just to introduce the issues. And then I'll talk about what's next, so where we are right now in the Ultracam project and where we are going. So firstly, the context. So as you know, when you use an ultrafast laser on a sample, here metal in the scope of this project, under certain parameters, under certain conditions, you can get what we call LSFLs, LIPS, meaning laser-induced periodic surface structures. There's an example. What's interesting is that beyond those topological structures, you also change the chemical characteristics of your surface. So here you can get, for different laser parameters, you get different topological and chemical characteristics, meaning on the macro scale, you get different colors. So now that we know that, there's of course the question of does the oxidation process play a role in the formation of those structures? For the type of those structures, being the HSFLs, we are talking about high spatial frequency, so lower frequency than the laser. There's been a discussion about whether or not it played a role, and previous PhD at Laboratoire Mercurial showed that we can obtain a lot of different, similar looking structures for many different parameters, but many different atmospheres. So oxidation doesn't play a critical role in the formation of those structures, at least. But it certainly plays a role in the long-term surface properties. Because as you can see here, if you irradiate under ambient condition, you get oxidation. So those two peaks indicate oxidized tungsten. So you've oxidized your sample under ambient conditions, which is logical. But those peaks don't appear in the vacuum, which is also logical. But what's interesting is that over time, there's a gap which stays constant over long periods of time, meaning that there's something fundamental about the oxidation process during irradiation that plays a role during long-term surface properties. Another work that's been done is with metallic glasses. Here, they're working with really low energy flux on the metallic glass, and they get nano holes, or nano wells as they call them. So those nano wells, what's interesting is that normally you get an amorphous layer of zirconium and copper oxide on the surface, but after a laser irradiation, you get a thick-ish, about 20 nanometers zirconium oxide, crystallized in this case, with no copper. So you get a preferential oxidation of zirconium, which can either be explained by an inward migration of copper or an outward migration of zirconium. When you increase the laser fluence on metallic, not the same composition, but on zirconium copper metallic glass, you get low spatial frequency structures, and you complete, dare I say, the migration of copper, the outward migration of copper. So you get zirconium oxide with preferential oxidation, but you also get pure copper, non-oxidized copper nanoparticles. That's really interesting because it means that you get outward migration of copper during the ultrafast process. So another about the, I'll put them in the chronological order. So still about the crystallization of oxides. Here, here you can see the difference between between the amorphous oxide, which has a native amorphous oxide, or the kind of oxide you get when you under laser irradiation. So you can crystallize the native oxide layer under laser irradiation. So to sum up the scope, the goals of the project. Firstly, there's going to be some ultrafast laser irradiation under controlled pressure and atmosphere condition. Mostly metal samples. I'll talk about what kind of metals we're going to use. Then there's going to be, we're going to try to understand the formation process of the structures thanks to topographic analysis and also thanks to chemical analysis, mostly done at Laboratoire Georges Friedel, so in Saint-Étienne, try to understand the chemical processes involved. Mainly oxidation right now, but we're open to other chemical processes, of course. And lastly, we're going to study of the potential for future applications. We've talked about either photoelectrocatalysis for CO2 reduction or surface placement coupling. So, me, Julien, master's degree in engineering in optics and photonic from Telecom Saint-Étienne, so this very building. And the PhD thesis, it's an international collaboration between Laboratoire Bercurien for laser expertise and structural analysis. We got the Laboratoire Georges Friedel, which is for the chemical analysis aspect and also their expertise in material science and metals. And lastly, the University of Ottawa for the potential uses, so meaning electrocatalysis for CO2 reduction and plasmonics. So UltraChem, as I said, ultrafast laser structuring, topological and chemical functionalization of surfaces. So what's already been done in a recent series of experiments, mainly done by Hugo Brouillet, which I think, and Chetong Xie, which was a PhD student from the University of Ottawa. So I'll just show some same images, some like electronic microscopy images which were done. So all the irradiation were done on copper because the University of Ottawa used it for CO2 reduction. We used the Pharos laser at 515 nanometers, and we used many different samples of copper, like with different roughness. This one is just post laser deposition target, which was used very early on to get an idea of what we might expect on copper. So we saw different structures. Here are nanobumps with a high spatial frequency. There's also partial low spatial frequency formation, and when you increase the fluence and the number of pulses, you get into the interesting area, which is this is ablation. So yeah, when you hit really hard, it's not really interesting. But when you get the right parameters, so right number of pulses for the right fluence and the right spacing between pulses, you get quite nice looking ellipse. Those are not the cleanest one we've got, but there's all, I wanted to all use like the same sample, but yeah. So after that, some AFM and FFT analysis were done, which gives us a depth of around 100 nanometers and a period between 350 and 500 nanometers, which corresponded to the demands by the University of Ottawa for their electrocatalysis of CO2 reduction. Another aspect is one of what was sort of rabbit hole that I went in recently is the question of high temperature oxidation. Because the main issue with high temperature oxidation is that almost all the papers that articles that have been written about it are on metallurgic and long-term high temperature oxidation. So you've got people heating bulk samples, big samples, and seeing an increase in millimeters of oxidation or micrometers, which is beyond the scope of what we're doing. But firstly, I'd like to talk about the metals that are in use for the African project that we are planning to use. So Elingham diagrams, I'm not going to go in detail about how they work, those diagrams, but what's really important is that the position on this diagram indicates the stability of the oxide under high temperature and low pressure. It tells you if the reaction is thermodynamically possible. It doesn't tell you anything about the kinetics of the reaction. So what I just want to highlight is the range of oxide stability that's already been done or that's planned for the Ultrafast project. We use zirconium oxide and copper oxide and tungsten and silver for later. That's been told. It's the next one we're gonna do. So I've talked about the issue of standard high temperature oxidation theory. So I need to at least talk about it a little. It's called Wagner's theory. Its main premise is that the migration of charged particles, so anions or cations, or their frequencies equivalent. So this is the migration of those charged particles drives the oxidation process. Mostly it's either one of the two. The original theory is that the two takes place at the same time, but calculation and numerical solving of atomic mobility shows that it's mainly one of the two, not the two at the same time. So the issue with this theory, I highlight those are the hypotheses you need to make to work in this frame. There's the three main that may not work under ultrafast laser irradiation. So firstly, this thermodynamic equilibrium, either at the interface phases or locally throughout the scale. This one, I think, we can accept, but the other one means that given that oxidation is an exothermic process, it means that we have the time to diffuse heat in the time scale, in the time frame of ultrafast laser excitation, which is uncertain. But the last one, which definitely is not true for many cases of ultrafast laser oxidation, is that this works for thick scales, meaning that you are the scale thickness is greater beyond in front of the electrical double layer or pi length. That's why I'm currently working on properly understanding and explaining the theory for thin films and ultra thin films claimed by Mott and Cabrera in 1949. So this is the next what's going to be doing. And finally, what's next? Where we at right now and we're going to do. So right now we're here. So between the first laser structuring that's been done and understanding the oxidation process. The next step is we hope to be doing in the next 6 to 12 months is understanding and try to do space-time and polarization control of our pulses to see more, dare I say, of the chemical processes. And then finally, unveiling potential for future uses. A 12 weeks at least mobility at the University of Ottawa is planned before the end of 2025. The exact dates must be set but that's where the talk is right now. So, well, thank you for listening. Please ask any question that comes to mind.
Thank you. Great project and great presentation. I was wondering about kinetics. So, because as you showed, temperature is quite important. But if the temperature doesn't stay high for a long time, then there's a limitation. You are bringing a few watts, but on a really localized spot, right? And then this net diffusion will move around. So, yeah, I think. Do you have more static?
So, if I understood correctly, the question is that are synetics, like, is the time frame of synetics an issue when talking about ultrafast laser irradiation?
No, I'm just suggesting maybe because we are going for a really stationary problem, stationary project, so have a limitation. And I was wondering, yes, because I guess the oxide you form is not only the one that is possible, but also the one you have time to form in the time frame where you have to measure after oxidation. So I was wondering if you are thinking of doing some temperature modeling.
So in previous works, I'm thinking mainly the one on tungsten oxidation. There's been some two temperature modeling done and molecular dynamics to get an idea of the time frame at high temperature, for instance. And so yeah, it's certainly in the project, but I just focused on what I've done in the 3 months, less 3 months. But yeah, it's definitely, we're on the same floor with the same team, so that definitely works.
Question: what is the temperature of laser radiation? High temperature solution. The internal.
So in the case of this article for tungsten, so where there's been a 2 temperature model and coupled with molecular dynamics simulations, the sample reached a temperature of, if I'm not mistaken, 6,000 kelvins and stayed above 1,000 Kelvin for about 7 nanoseconds. So you get, on at least for tungsten, you get a cooling that takes about maybe 1 to 10 nanoseconds before it goes back to ambient temperature. So this is another issue which I didn't talk about, but yeah, it definitely reaches conditions where it should be melted, but the time frame at which it's in those states is so short that the question is, can we really talk about a liquid? It's mostly like ultra dense matter, and yeah, that's another issue because most of the oxides have a higher temperature, have a higher melting point. So at one point you should have a melted metal with a solid oxide above it, and I believe the hydrodynamical phenomena that explain many of the structures formation, those are true. So how do we get a uniform oxide layer if at one point it's solid on a liquid layer?